Alright, welcome everyone. Let's talk about ionic bonding. This is the first of three types of bonds we're going to learn about. And we're also going to address a couple sort of related topics. Let me adjust that. So, let's talk about what an ionic bond is. So, an ionic bond is a bond that forms when a metal, remember that distinction we learned about from the last lecture, that's the left side of the periodic table, donates one or more of its valence electrons to a nonmetal. Remember, those are the ones on the right side of the periodic table. What do I mean by valence electrons? You should know all about electrons at this point, but what's a valence electron? A valence electron is simply the electrons in the outermost electron shell of an atom. Okay, so when many of you were drawing your posters, for example, you might have drawn your sort of a little nucleus of, let's say, carbon. Okay, you would have 6 protons and 6 neutrons in here, and then when you were drawing the shell, the electrons, you had sort of a first orbital that just had 2 electrons in it, and then you had a second orbital that had 4 electrons in it. Okay, and this outer orbit is also called a shell, is where the valence electrons are. So in the case of carbon, you would have 4 valence electrons, all right? We're not going to worry too much about how to count them or where they come from or why they're in that configuration. That's all stuff for chemistry. But just know that the valence electrons are the outermost electrons, and those are the ones that are used in bonding, mostly. All right. So, when I say a metal donates one or more of its valence electrons to a nonmetal, what I mean is that so a metal, well, you'll see on the next slide a good illustration of it, but a metal loses one of its outermost electrons, and that electron sort of travels over and fits into the electron shell of a nonmetal that gains electrons. Okay? So all of this is to get a stable outer shell, which is why they prefer to do this. Okay, so let's look at I should mention the simplest written form of a ionic compound is technically called a formula unit instead of a molecule, because there's no such thing as, like, if we're talking about a salt, so NaCl is a classic example of an ionic compound with an ionic bond, but there's not really ever just like a bit of NaCl floating around. Like you could have a molecule of like carbon dioxide floating around, but you're not going to have just one pair of sodium and chlorine floating around together as one molecule. They're usually in groups of much larger ones. So technically this is called a formula unit instead of a molecule. And as I just said, typical ionic compounds are alkali, so remember the alkali metals, it's that first group on the left, and halides, which are the halogen group, that second to last one right next to the noble gases. Example being sodium chloride. Okay, so this is a good picture of what's happening when you make sodium chloride. All right, and this is how an ionic bond forms. You've got a sodium atom, and once again, you've got on the outer shell of the sodium atom just this one valence electron sitting there by itself. Atoms want to have a nice stable outer shell of 8 electrons. Okay, this is called the octet rule. That's on a later slide. So, in order to get that, it's very easy for sodium to kind of just get rid of that one pesky electron that's sitting on its outer shell, and it would like to do that to become more stable. This sort of opposite is true for chlorine. All right, chlorine has 7 valence electrons, whereas sodium has 1 valence electron. Okay, and you can do the math here. If this valence electron were to travel over there, and chlorine would have 8 in its outer shell, and sodium would sort of get rid of that outer shell and have a nice stable outer shell of 8 underneath it. Okay, and that's demonstrated over here. Nice stable shell of 8 and a nice stable shell of 8. Okay, but losing an electron turns you into an ion, right? Remember, that's when you have a non-neutral atom because you have a different number of electrons versus protons. Okay, so now sodium has one more proton than it does electrons because it just got rid of one of its electrons. And so it's positively charged. And the opposite is true for chlorine. It gained an electron, so it's now negatively charged. Okay, and this is where the actual bond comes from. That thing before, this first step, step 1 over here, that doesn't really have anything to do with bonding. This is just having to do with wanting a stable outer shell. But step 2 over here is that these two things, because this is negatively charged and this is positively charged, they attract one another just due to the fact that things that are positively charged and things that are negatively charged attract one another. We're going to get to that in basically the last unit of this semester, but just know that the actual attraction that holds ionic compounds together, the actual ionic bond, is just an electrostatic attraction between things that are positively charged and negatively charged because one of them has given some amount of electrons to the other one. Okay? And so this is sort of just another example of that. Right? So, if you'll recall, when we were doing the notes on the periodic table, let me hide my webcam here so you can see that better. When we were doing the notes on the periodic table, I gave you these numbers up here, right? These ones. +1, +2, +3, nothing, -3, -2, -1, and 0. Okay, these numbers along the top. And I sort of didn't explain the numbers at the time. Well, here's where the numbers come from, okay? Because, let's take oxygen down here as an example. So this is oxygen. Alright, oxygen has 6 valence electrons, 6 electrons in that outer ring, and it would like to get 2 more, right? Because the octet rule says they want to have a full outer shell of 8 electrons to be stable. Okay? And so the easiest way for oxygen to do this, I mean, it could lose all 6 of these electrons, which would reduce it down to its innermost shell, which only has 2. But it's much easier to just get 2 more electrons, right? Just get another 1, get another 2, and then boom, you've got a nice stable outer shell of 8. Okay? And that is where this number here comes from, right? Because if I gained 2 electrons, but I kept the same number of protons, all right, then I've got 10 electrons, you can count them down there, and 8 protons, which means that I have -10 charge from the electrons, plus 8 from the protons, and that gets me a total charge of -2. And that is where this -2 charge comes from for all of these elements in the oxygen group. It's all the same logic. They have an outer shell with 6, they would like to get 2 more, and that causes them to have a ionic charge of -2. Okay, and the logic is exactly the same here. Alright, they've got an outer shell with 3, they want to get rid of those 3, and so that causes them to be positively charged by losing 3 electrons. Alright, so that is just a background on where those oxidation numbers, as I referred to them before, or just ionic charges, where those come from and why they're associated with the different groups like that. Okay, let's bring me back here. Alright, finally, talking about ionic compounds. The ionic compounds themselves are neutral, meaning that they have 0 total charge. Okay, so the example from before, we had a sodium, which was +1, and a chlorine that was -1. Remember that if there's no number up here, if it's just something plus, that's the same as being +1, and the same for the minus. If there's a number up there, like something 2 plus, then it's +2. But if it's just the plus, it's +1. Just the minus, it's -1. So, the sodium has +1, this chlorine has -1. Okay, so they cancel out, and you get, +1 -1 equals 0. But it can get a little more complicated than that, right? So an example of one that's also pretty simple, but just so you have seen it, let's say cadmium is from the group that has a +2 ionic charge, and oxygen, as we just saw, is from the group with -2. Okay, so these two will combine just fine because we've got +2 offset by a -2, and they will come together and have a compound that looks just like this, cadmium oxide. All right, and we'll worry about the names later. But what about something like this? Aluminum oxide. So if we look up aluminum, remember that's in the group that gets +3, and oxygen is still in the group with -2. These two can go together. This is aluminum oxide is just rusted aluminum, for example. Or, well, it's a little more complicated than that. It's also bauxite, if you've ever heard of that. Let me just write that. Bauxite. Anyway, that's just an aside. So how do these come together? Well, we need some way to have the aluminums add up to the same as the oxygens. And we can't really do that with just one of each, right? If I just had AlO, this would be +3 and -2, and I would still get a +1 out of this. That can't happen. So the way you do this is you just have more aluminums. You change the number of aluminums and oxygens that are in there. Okay, so the way we do this is we kind of crisscross the charges, all right? So the +3 comes down here, and the -2 comes down here. So we get 2 aluminums and 3 oxygens. Okay, so let's check that that makes sense. The aluminum, we have 2 charges of +3, which is +6. And then for the oxygens, we have 3 charges of -2, which equals -6. So those cancel each other out, and that works. Okay? Another example of this principle, like that's kind of the most complicated it's going to get, but you can also have like sodium oxide, right? Sodium is +1 and oxygen is -2. So we crisscross the charges again and get 2 sodiums but only 1 oxygen. So we've got +1 times 2 and then -2 times 1. So we've got a +2 and a -2. They cancel each other out, and that works. All right. So we will practice that a little more, but that is, the hardest part about ionic compounds is figuring out those little subscripts to make the charges work. All right, and I believe, yep, that is all. So that's your intro to ionic compounds. Covalent compounds, or covalent bonds, and metallic bonds are coming next. All right, I'll see you in class.